The year is 2026. It's impossible to go outside without hearing people talk about artificial intelligence. By now, you've probably heard people say AI will impact business in many ways, but for most people, what that actually looks like is still unclear. So in this video, I'm gonna walk you through a concrete example of automating a simple task using a branch of AI called reinforcement learning. When most people hear reinforcement learning, they think about robotics or video games. But RL is just a way of building systems that take actions to achieve a goal, and it can be useful in many other applications. RL uses a learning loop where agents interact with the environment. The agent is the decision maker that interacts with the world and learns through trial and error. The environment is the external world the agent inhabits. The agents observe the current state of the environment and use the information it contains to determine their next action. Actions are choices an agent makes to interact with the environment. The feedback the agent receives are the rewards, which measure the success of its actions. To make everything concrete, we'll begin with a simple example, a cookie shop. In this scenario, customers arrive, place orders, and wait for their orders to be fulfilled. Behind the scenes, cookies are baked in batches. We always need to bake enough cookies to keep our customers satisfied, but having a large surplus leads to waste at the end of the day. On the other hand, if cookies aren't readily available and customers have to wait too long for their orders, they will cancel them. Now imagine we've built an automated cookie baking machine. The key question is, when should it bake more cookies? Instead of hard-coding rules, we'll use reinforcement learning to allow the baking machine to learn an effective baking strategy on its own. Over time, it will develop intuition about how many cookies to bake and when to bake them. Before we do any reinforcement learning, let's define how the system functions. Several components impact the cookie shop environment. First, we have customers who can make their orders in person or online. This determines how long the cashier spends preparing their orders and also their willingness to wait. The customers can order a predefined number of cookies, which of course impacts our cookie inventory levels. And to fulfill all of those orders, we need a mechanism for making cookies. In our store, we're buying a machine that will make the cookies for us automatically. To apply reinforcement learning to our cookie shop environments, we need a model to represent the interactions between the customers, the cashiers, and also the inventory of cookies. In our case, we will use a custom-built discrete event simulation to build this model. A discrete event simulation is a way of modeling a system where things only change when an event happens. For example, imagine our cookie inventory starts with 20 cookies at time 0. A customer arrives and places an order that takes 2 minutes to prepare. If they order 1 cookie, we jump the clock ahead to 2 minutes and update the inventory. Now we have 19 cookies. This type of model is very useful because it naturally captures queues, resource constraints, delays, and variability. It can also provide a structured environment where a reinforcement learning agent can observe the system state, take actions, and learn from the consequences of those actions. In the case of the cookie shop, we'll define the agent as the machine responsible for making cookies. The environment will be the cookie shop itself. The agent will take actions that define the number of cookies being made, and the environment will respond, giving rewards showing how many orders were canceled. The agent will be able to see the number of cookies available in the inventory as the state of the system. This is what this looks like in practice. Using Python's SymPy library, we built the backbones of the cookie shop. First, we implemented a function that creates the orders of all customers. This function defines the customer type and the number of cookies in each order. Then, we built a function that fulfills those orders considering the queue of customers, their willingness to wait, the time required to process each order, and the number of cashiers available. And lastly, we wrote a naive implementation of the baking machine that bakes cookies at fixed time intervals. This will allow us to compare the naive implementation to the performance of a reinforcement learning agent. Let's see how this cookie shop performs. Here, we connected the model we just created to a dashboard so we can track the metrics that are most important to the success of the store. On the left of the dashboard, we have all of the inputs required to run the model. This includes arrival rate of customers, ratio of online orders, number of cookies in each batch, time required to bake those cookies, and number of cashiers at the store. The last input defines the probability of a customer ordering a fixed number of cookies. Now let's go ahead, change some of the model inputs, and see what metrics we can get out of it. I'll first change the number of cookies per batch to 25 and the time required to bake those cookies to 15 minutes. I'll go ahead and press run so we can take a look at our model outputs. So this is what our results look like. We see that the top 3 boxes in the dashboard give us a summary of how the day went in the cookie shop. The leftmost box will show us a breakdown of the orders at the end of the day, and we can see a pretty large percent of orders got canceled. In the middle, we see the number of cookies left in the inventory in the end, and on the right, we can see the average customer wait time throughout the day, which was also pretty high. The rest of the dashboard will show several metrics over time, like customer wait time, cashier utilization, number of cookies sold per hour, and also the number of cookies in the inventory. In general, we can see the inventory of cookies was pretty low throughout the day, and that really drove the large customer wait time and also the number of canceled orders. Because some of our model inputs have randomness within them, every time we rerun this model, we get slightly different outputs, as I'm showing on the screen. However, what we can see is that we consistently get a pretty large number of canceled orders and also pretty high customer wait times. Let's see how we can use reinforcement learning to change that. In the introduction of this video, I showed the reinforcement learning loop. We'll break it down step by step. Imagine an agent is in a given state. It takes an action and receives a reward. Then the environment transitions to a new state. From there, the agent repeats the process, choosing another action and receiving another reward. But the agent could have taken a variety of different actions at every state, with each one of these paths leading to a different total amount of reward. Through repetition, the agent needs to figure out which series of actions lead to more rewards. Whenever the agent is in a given state, it must consider how much reward it can expect in the future by taking any action right now. The estimate of future rewards is called the value function. The simplest way of thinking about this is to build a table of scores. When we're in a state and we take an action receiving high rewards, we increase the score. Otherwise, we decrease it. As the agents iterate on the learning loop, the scores are updated based on the rewards received until they converge towards the true value of taking an action in each state. Each time the agent is in a certain situation and chooses an action, it looks up the current score for that combination. This builds a policy of how to select actions. In general, the policy will select the action that maximizes the value function. To summarize, this value function can be defined as the expected cumulative future rewards the agent can obtain by taking action A in state S when following the optimal policy. That is, if I take this action, this is how much reward I can expect to get in total going forward. There are many algorithms available to update our estimate of this value. In this video, we'll use the Q-learning, which considers the reward you get immediately plus the value of the best decision you can make next. Many factors are used to update our estimate of Q. The first is the immediate reward, which tells the agent how good the last action was. The second is the estimate of the best future Q from the next state. The third is the discount factor, which determines how much the agent values future rewards compared to immediate ones. If the discount factor is high, the agent thinks long-term. If it's low, it will focus on short-term gains. And lastly, there is the learning rate, which controls how quickly the table of scores are updated when new information comes in. To set up these concepts in code, we modified the cookie shop discrete event simulation to fit the needs of the RL training process. To be able to rerun the simulated day several times, we first added the ability to reset the environment to the start of the day, considering the model inputs we're training our agent for. We also added the ability to step through the day at fixed time intervals. This allows the agents to interact with the model by taking actions and receiving feedback. We also had to define the actions, states, and rewards. Here, the actions are the number of batches the agent will make at a given step. And since our goal is to train the agent to reduce the number of customer orders that get canceled due to stock shortages, we define the states as the number of cookies in the inventory and the rewards as the opposite of the number of orders canceled in the last time step. This means the agent will have a greater reward if it makes enough cookies to satisfy all the orders. To obtain a policy for how many cookies to bake as a function of a given state, we start by initializing the queue table. Next, we define the parameters required to update the values in this table using queue-learning. Note that we defined an initial value for alpha. This value will be decreased as the training progresses. The idea is that initially we'll make large updates to our estimate of Q, but over time we will only make smaller adjustments. To implement the RL training loop, we determine the number of simulation days the agent will experience, known as the number of episodes, and the maximum number of steps per episode. In our case, steps are naturally limited by the simulation length, but since this is common practice for general RL environments, we'll include it in our setup. For training, we will allow our agents to select actions using an epsilon greedy strategy, meaning it usually picks the best known action, but with epsilon probability, it chooses a random action. This allows the agent to learn but continue to explore the environment around. The probability of taking a random action will decrease as we train our agents. And finally, we put it all together. For each episode or day at our store, we will reset the environments, update alpha and epsilon. And for each step in a given day, we will select an action, collect rewards, and update our estimate of the value function. The result of this iteration will be an estimate of the value of taking each possible action at any given state. We will add this estimate to the cookie shop and run the simulation again. Now in every scenario, the agent will select the action that maximizes the value function for that state. When we run the simulation with the RL agent in most runs, like I'm showing on the screen, the number of canceled orders drops to 0. Occasionally, we see 1 or 2 cancellations, but overall, the system does a very good job of keeping customers from walking away empty-handed. If we compare the performance of the model before and after the RL agent was used, we can see that its strategy is to keep inventory high. The advantage of this approach is that by having cookies always available, customer waiting times goes down and cancellations are rare. But there's a drawback. At the end of the day, all the cookies left on the shelf are thrown away. That means wasted inventory and lost profit. So while we solved the problem of cancellation orders, we introduced another one. So let's modify our agent reward structure to change that. To improve the system, we'll expand what the agent can see. Instead of only knowing how many cookies are in inventory, it will see the timestamp it's in. In addition, we'll adjust the rewards. For most of the day, the reward will be equal to the negative number of canceled orders, but during the final time step of the simulation, there will be a penalty if the number of cookies left in inventory is above 50. Now, let's run the updated model and see what happens. The dashboard shows how, in general, the model that penalizes for wasted cookies has smaller number of cookies in the inventory, but every once in a while this number is very high. This is likely due to the randomness in demand at every model run. The improvement in waste comes at the cost of number of canceled orders, which is often a bit higher than what we had before. This shows how the new reward structure impacts the agent behavior. So what can we take from all of this? The example in this video was simple, but it showed how to set up an RL algorithm to work for a real system. We saw how to define the environment, action states, and rewards to train the RL agents. The example also showed how changing what the agent sees and the rewards it gets can affect how it behaves and how close it gets to reaching our goals. This is just one way AI can help you with your daily tasks, even if you're not building a fully automated system. So tell me in the comments, what are some ways you think you could use this method in your day-to-day?